Oh, funny story. So I was under the impression from the warden last night that I was going to be helping move at church and it was going to be like a 3 hour ordeal. 20 minutes. I was done before 6 p.m. So we could we could have still had class. In fact, I thought about, because I was here in Mequon, I thought about slacking it and just saying, hey, if you want to show up, we'll record it. If you can't make it, fine. But then I didn't because I get to go have Chinese food. So it was not that hard of a decision at the end of the day. But I assume you were upset that. Really, really, really. So you wanted to sit in class for 4 hours? Yeah, no, I get it. It makes sense. Well, we can reschedule. We could do it tonight. Like, why don't we do it yesterday? Or maybe we'll go 6 hours the next 2 weeks. For 1 week? Yeah, you make all good points. All good points. Okay, so let's see. Homework assignment was to do left, right. Okay, how'd that go? Not too bad? Oh, okay, good. All right, so let's run this real quick and see what the current state of the world is. Well, that's starting there. All right, so we figured out last time how we are out of balance, right? And then we need to actually ask a tree to rebalance itself. Did we start the function yet? Or that's where we're at?
We just had it so that it would tell us which way it was unbalanced.
Right. Well, we didn't start the function. Sometimes I put the like, this is where to fill in your answer for the homework. Okay. All right, so our binary search tree tells us how we're out of balance. So once we're out of balance, then we need to determine how we can fix that. And as we're adding stuff to our tree, is out of balance. So for this one, we only have to do left, and right. So let's get ourselves back into a situation of left for how we're out of balance. Let's go back into this guy. And let's do tree traversal. All right, so we need to go back to our original. So FBG. And then AA should get us out of balance. That should be left out of balance. Is that right? Oh, thank you. How are we out of balance related to A should be left. That's the last guy we passed in. Okay. All right, so now that's our tree, which is our BST. So we're going to go ahead, and since it's true and we're out of balance, we know the last guy we supposedly know the last guy we wrote in there. So when we go into BST, let's squeeze this down. Here's when we add our payload, and we always have a binary tree as the last guy. Well, when we try to add a payload, it's a char, but he ultimately gets turned into a binary tree either here. So root here would be a binary tree, or when we add to a binary tree something, currently our add function returns nothing. It might be helpful for us to receive the binary tree associated with the guy that we added, potentially. Thinking about how we can do this organically. If we come in here, let's draw this picture. Recent 300. All right, so this is our current state of our tree. Looks like that. All right, so we just determined that we're out of balance, and this is the last guy we added. So that's what we've artificially done. All right, so once we add this guy, we can go ahead and we can, this guy ultimately becomes a tree. So let's think about fixing a left-left. We'll give ourselves the algorithm for this, and then we'll decide which players do we need here. Each of these are binary trees. Which players do we need in order to fix this? All right, so for a left-left, what do we do? Let's look at our picture for AVL trees. Here. Here's our left-left case. We ultimately want to rotate. So if you think about kind of grabbing onto the 4 like it's a doorknob and turning it to the right. So we're rotating things about the 4. So this guy becomes the new local root, if you will. Okay, so who do we need to know about related to this, this 4? Keeping in mind that the guy above this is still part of a larger tree. Okay, so if we think about it in our picture here, okay, we ultimately want to produce, let's just write a second version of this tree. We ultimately want to grab A as our rotation point and effectively do that. Right? That's what we want to end up with in a left-left case. Okay? So we need to discover the node immediately, well, the tree immediately before the tree we just added. All right? Now, once we have that, so we need to discover the pivot point. So that's what we're going to label this guy. So that's going to be our pivot. Draw a little arrow on him so we can keep them separated. All right. So that's our, I'll just get rid of that for right now. So this is our pivot point. So once we get to our pivot point, that is the guy who's immediately before the guy we just added. What do we do with that? Well, we need to know about the guy right before him, right? The parent tree. So for right now, let's just call that parent. And we know this person must exist. Because we can't be out of balance by 2 if the pivot point doesn't have a parent. Now keep in mind that currently this parent is connected to his parent in our picture, which isn't necessarily guaranteed in every tree, but consider it in this tree. So that means if we just haphazardly drop this guy down here, this guy still points to this guy. All right, so we're still, this guy's left points to this, where we really need him to update to this guy. Oh, let's just go with that. All right, so step 1, let's write the algorithm. Left, left, algorithm. Identify pivot somehow. So that's our pivot point. Then what? Identify the parent of the pivot. Fair enough. All right, so the first thing I'm considering here is that we're walking down the left side of the tree. Since we know we're out of balance left, left, I can keep going down left, left, and I'm going to keep track of where I've been as well as where I'm going to go next. That way I can get those three variables. So this guy, if we think of it, this is kind of bucket 0. This is bucket 1. And then our leaf node, the guy who we just added, is the bucket 2, if you want to think of it like that from this picture. Okay, so we've identified the pivot, we've identified the parent. This guy doesn't really matter at this point. He's the guy that ultimately threw things out of balance, so he's the culprit, but we don't really do anything special with him in this model, right? He just kind of gets drug along with this guy. He stays the pivot point's left child at all points in time. All right, so now the parent is going to become the pivot point's right child. And then the parent's parent, or grandparent, will become the grandparent's left child, if the grandparent exists, will become pivot, which then frees up parent to be dropped down into position here. Make some sense? So we're going to identify pivot, parent, grandparent. So let's take out the bucket stuff for right now. Now the grandparent to pivot could be null. It's possible for that guy to be null. That is to say that if my tree did not have, let's just move this down here for a second. If my tree looked like, that, we would have been out of balance one level earlier, which means pivot would have been parent. Parent would have been grandparent, and grandparent doesn't exist because we're up at the top of the tree. Okay, so grandparent could be null. So we definitely need to check that before we just haphazardly set its left child. So if grandparent is null, what does that mean? What do I do in the event that grandparent is null? Who's the new root of the tree? Pivot, right? So if we draw this like this, grandparent points nowhere, parent currently points here, pivot currently points in the here. If that's what our picture looks like, we're going to still drop parent down to the right child. That happens 100% of the time in a left-left case. Right? But pivot now becomes the new root node, which means we need to tell BST to set his root to pivot instead of what it used to be, which was parent. Make sense? So we're going to have access to the top level binary search tree. So that means we either need to pass it along to our binary trees under the line, or set a singleton to keep track of our top level BST so we can get back there from anywhere down in the tree. So if I'm right here, if I'm sitting at this binary tree in my tree, and I need to access the governing BST that is in charge of this guy that knows about the root node, which would be him, I either needed to pass that BST along from function call to function call to function call, or we can do the cool kid thing, throw it in a singleton, and now we have access to the BST. Make sense? All right, which route did we take with our homework assignment? None of those? We didn't pass the binary search tree or the binary or use a singleton? None of you? How did you handle setting a new root for a BST? Very very talkative group today. So tell me, how did you handle this? If you didn't pass along the BST and you didn't keep track of the BST in a singleton, if you were in a situation like this where you have a left out of balance, which this would be, right? This is left out of balance, and we need our pivot point to become the new root, and this entire thing is governed by our variable of type BST. Okay, so a BST is this entire thing that happens to have a root node that points to the same place as parent right here. But each of these guys individually are binary trees. How do we let BST know that his new root is pivot? How did you guys pull that off in your homework? Or did you not do that part of it? Okay.
I was just going to use like a placeholder variable to kind of swap them around within the function. So it wasn't a singleton.
Okay. But you can see how a singleton would have been beneficial for the top level. Who got this part working? Let's go that route. That way I know who to target. Nobody got this part working? When I asked how the assignment went, we got a whole lot of nods, like, oh yeah, it went well. So when you really say it went well, you mean it went horribly terrible? Is that like the best? Go ahead.
Well, I did get it working, but I did exactly what she said. I just created a variable, stored the binary tree that we're wanting to have be the new root, and then stored the old root, replaced the old root with the new root, and then passed the old root to the new root.
Okay, so you kind of pass things along from function to function, which is fine. Yes, I mean, that's called injection. So you were injecting the pieces of information that you needed to know. So if we're kind of, scaffolding down this, or I guess traversing down our tree here, and we're kind of hanging right here, and we need to know about stuff that happened above us, we kind of have to bring that crap with us, right? That's one option. The other option is to store it inside of our singleton so that we always have grab access to it if we need to access those things. Both of them are viable. It's not like that. It's not like one is horrifically better than the other. In fact, maybe it's this type of thing where with great power comes great responsibility. So singletons, with all of their convenience, can often become the overcrowded garage of your application. If you throw everything in a singleton, you end up having this really, really scary looking singleton. Okay, let me actually show you an example. I'll show you an example in this application where too much stuff was thrown into the singleton. So here's our singleton right here. It's a lot of crap in the singleton, to the point where it's hard to decide at any point in time, do I throw something else in that garage or do I keep it local where I can remember what happened? That makes some sense? So singletons are not the save-all for everything. In this particular case, given what we're trying to do, I think a singleton makes a lot of sense. All right, so what we're going to do is right off the bat, before we identify our pivot, we're going to store the top level BST in a singleton. Okay, and we can do that when our binary search tree is first born, right? Because his root value is a pointer that points to something. So really, we're just setting up that pointer so that we have access to it. So maybe we can actually say the top level BST. Well, we'll have access to his root from there. All right. Then we'll identify the pivot. Then we'll identify the parent. Then we'll identify the grandparent. All right. So we're sitting here, so let's, whoa, I actually didn't expect it to jump between slides like that. Oh, that's weird. I didn't know it did that. I guess in my mind, I thought that once you return to a slide and you did an undo, it would undo on that slide, not what you previously did in the application, but I don't know if I have a real great reason for believing that's the way it should work. That's the way it works in Xcode. If I switch from file to file, and I think it's the same thing with Eclipse. If you undo in a file and then you go to a different file and you undo there, it'll undo the last thing you did in that file, not the previous guy. Yeah, I just assumed that it would work that way. Yeah, for no great reason. Just that's what I assumed should happen, because if I were writing this for this exact example, and it would only work for this, that's how it should work. All right, so let's go back down to our case where our grandparent is not null. And let's think about identifying these various dudes. All right, so, and here we'll, as a facade here, woo. Okay, I think that gets us out of balance the right way. Okay, that's left out of balance. All right, so imagine the larger tree that we're dealing with here, where we are out of balance left because of this last insert of this A. Okay, so we've identified that we're out of balance left. Code already does that. We know how we're out of balance. So now we need to identify these three dudes. Now, when we're looking at it here, it was like, oh, well, just the left node is the grandparent, the right node, the left of his is the parent, the left of his is the pivot. Well, we actually need to go all the way down to the bottom and then work our way back up, right? So we need to figure out how many levels down we needed to go, because we need to identify these three guys. Get pivot, get parent, get grandparent. All right, so what is pivot? Let's just think about identifying pivot initially. How do we find pivot? Go ahead. Okay, so one up from the leaf node, or the node that was the culprit here, the guy that knocked things out of balance, right? But how do we go one up? Our binary trees don't have previous nodes, right? Could they? I mean, given our current tree, let's solve this. Let's solve this the two different ways. We'll solve it the way where we're not going to modify our tree structure. That is, what we need to do is we already have some code that finds the actual culprit, right? So we have that guy. In fact, let's go ahead and we can go and grab him here in a second. So we know how to identify this guy. And remember last time we had some of those situations where we were wondering if we had a false positive here? Because we know the guy who knocked things out of whack will be a leaf node. That is, his left and right child will not have a left and right child, or his left child, at least in this case, will not be null. That's how we know this guy is a false positive. So we can run down the entire tree and get to here, keeping track of the actual binary tree that is the culprit. Okay, so we can even label that guy if we want. Culprit. How do you spell it? Yeah, it looks right. All right. Now, he's not involved in the rebalancing system other than everything is relative to him for pivot, parent, grandparent. All right, so after we identify culprit and traverse down to culprit. So, when we identify him, what we really want is we want a pointer that points to the culprit. Then we want to run down our tree and find the dude whose left child is equal to culprit. That's our pivot. Then we want to run down our tree and find the dude whose left child is equal to pivot. That's our parent. Then we want to run down the tree and find the dude whose left child is equal to parent, if that person exists, if that binary tree exists. So we can do this iteratively, where we find culprit, then we do the exact same process again, where we find pivot relative to culprit, then the exact same process each time starting at the top of our tree. Right? So we're effectively doing the same thing 4 times. Not the end of the world. Traversing through a tree doesn't take that long as the tree's not that big. And in this particular case, we do directionally know where we're going. In a left-left situation, we know that we can just keep going left, right? Or do we? We know ultimately the last move was left, but we might have some right bobs and weaves in there to get down to that place, right? We just know that the first left means it's in the left half of the tree. The second left means it was the last turn, as we referred to it before, the last way we went to get to that point. So having said that, would it be beneficial, as we're kind of ping-ponging down through our tree, adding a node that might put things out of balance, might it be beneficial to store this guy as that's happening in that singleton? Kind of remember the would-be culprit. Okay, he's not actually the culprit in the event that we're not out of balance, but if we do get knocked out of balance, might it be helpful to find this guy, to know about him? Okay, now in preparation for rebalancing on a left-left at least, and we'll have to think about repurposing things, could we also keep track of the potential pivot every time we add something? A potential pivot is always the guy immediately before the culprit. Could we also keep track of the potential parent? At least in our world right now, in the left only situation. Okay? The potential parent could be kept track of. And then could we also keep track of the potential grandparent? So could we put those 4 things in a singleton and then just keep updating their values as we're in the process of adding a node to or adding a binary tree to our tree? That would be kind of helpful, wouldn't it? All right. So we're going to store the top level BST in our singleton. We're going to, let's do identify culprit. This is in singleton, in singleton, in singleton, in singleton. All right. So culprit is always the guy. So let's just think about culprit for a moment. Culprit's always the guy we're currently adding. So right now this tree is not out of balance. So our last add did not knock it out of balance. Now we're dropping the A onto the top of the tree. We're playing Plinko, right? Okay, and it's going to drop to the left. Then we're going to go to the, so as soon as we add it in here and we say add, as we're adding a tree, we're setting culprit equal to that tree. So culprit is following this guy down, and ultimately he lands when we finally hit a node whose next child is equal to node, or to null rather. All right. whose left tree, I guess, is the right way of saying it. And that ends up being our culprit. We just keep updating culprit as we go down the tree. All right, so let's start with just that piece. So we'll go into our code here.
Would it be fair to say that the culprit's left and right tree is equal to null? Or just the left tree?
Well, if we're checking our tree for being out of balance every single time, your culprit should always have empty children. Yeah, but you might have other binary trees in your BST that also have empty left or right children. They're also leaf nodes, but they're not the culprit. Okay, so you don't want to have falsely identify them. Oh, we're not in Eclipse. We're here. All right. So right here, when we're adding a payload, this is where everything starts. We know that this will never knock something out of balance, correct? That's not going to knock stuff out of balance if we're creating a brand new tree. So now we have a depth of 1. Let's go ahead and have we created a singleton yet? We have not. So let's go ahead and we're going to right click. I'm going to create a new Java class. Don't be fooled. I think I've talked about this before. They have a singleton object you can create. I hate the way it works. So I always create my singletons as just a plain Java class. So we're going to call this BSTCore. BSTCore. Oh, I like that. All right. And we're going to put in here static binary tree culprit. And we could start that guy off at null if we want. All right. So that is our starting point there. Static binary tree culprit. Okay. Now, as we are adding stuff, we don't need to keep track of culprit here. I mean, we can if we want. So we can say this dot, or I'm sorry, BSTCore dot culprit is equal to this dot root. We know we sort of just wasted our time setting culprit because we'll never be out of balance on a tree of just a root node. Okay, but at least this gets the ball rolling so we can actually steal that little equal sign there, just so we don't have to type it again. So otherwise, we're going to follow the rabbit hole down. So we're asking our root node, if we're not the empty tree, we're asking our root node to add a new payload. So that's a binary tree. So here's our add payload. Or, add takes our char. If it should go to the left, we're asking if the left tree is null. If it is, this is where this guy actually gets added. So culprit is equal to this dot left tree. Otherwise, we're going to go ahead and ask our left tree to add this. If it's our right tree, culprit is equal to this dot right tree. All right, so only when we finally land a node or land a binary tree do we set that guy to the left or the right tree. All right, so now we should always know about the potential culprit. That makes some sense? All right, so just to prove that, let's go ahead back into our main activity. So we're seeing how that's out of balance there. So after each add, let's go ahead and system.out.println BSTCore.culprit .get payload. So we should see FBGAA for our culprits each time. Just proving that we were able to kind of keep track on the trees that we added. Okay, so let's go ahead and run this, FBGAA. And that should come out of before the whole out of balance thing. We're just proving that we have access to those. FBGAA. All right, so now we know that culprit. All right. So now let's think about the guy one up from culprit. Hey. Guy one up from culprit is our pivot. So we need to keep track of our pivot. Potential pivot. So we'll go into our BSTCore. Add another guy in here. Call that guy pivot. All right. So now, as we're adding stuff, here we'll start at the very top here. In the event, I mean, I don't think we need to do any more here. We were just proving kind of how that worked. I mean, we could say BSTCore.pivot is equal to null if we wanted to here, just to kind of get the ball rolling, but we're pre-writing them as null there. So we'll chase it down our binary tree. So when we add stuff, woo. Right. When we add stuff here, this guy becomes the left tree. But if we can't add it here, we don't know about our culprit, before we leave this particular tree, we can go ahead and set the pivot, potential pivot, right? So if, well, I'm going to throw an if statement here in a second. So we'll say BSTCore.pivot is equal to this. Okay. This particular tree, the one that we were not necessarily able to set the left tree for, is, as far as we know, the current pivot, the guy immediately before. All right. We'll do the same thing down here. So we'll keep track of our pivots. Now let's go into our main activity. Now each time through here, let's go ahead and print out the pivot after we add something. So the first time pivot should be null. The second time pivot should be F. The third time it should always trail. Actually, not necessarily trail. It should be null, then F, then F, then B, then A. Because it's always going to be the guy immediately before, and since our tree kind of fills out evenly at first, we're going to have duplicate pivots a couple times through. So it should be pivot followed by culprit for each of those guys. It says it launched. Oh, this crashed the program? Oh, it's because I'm trying to get the payload of a null guy. So we're going to say if pivot not equal to null, and it's BSTCore.pivot. Then we could say that. Else, we can say system.out.println BSTCore.pivot, and that'll give us the null instead of trying to grab the payload of something that's null. All right, so null at first, then F. And the pivot for, oh, because we were able to add it right onto the F, so we set as left child, so that's why it's still null. So that's the B. G was to the right of the F, that's why the pivot is still null. Yeah, we actually could. We probably should be setting the pivot in either case. So we're setting the pivot to this right here, but in actuality, every single time through, we should always be setting this particular guy to the potential pivot, regardless of whether we added it directly to our left or added directly to our right. We're still the potential pivot. Even though if we added directly to our left and we weren't out of balance before, we're probably not still going to be out of balance, but we might be. So we always got to keep track of pivot. Now when we run this, this should be more correct. We'll lose out on a couple of these nulls, and they'll point to the guy immediately before whether we need him or not. All right, so we only have null the first time because there is no pivot before that. Then the pivot for B is F, the pivot for G is F, the pivot for A is B, the pivot for this A is A. All right, so now we're keeping track of our pivots, our potential pivots. Okay, let's keep walking up. What about parent? So now we need to keep track of our parent. How do we know about our parent? How do we add them into the mix here where we're adding stuff currently? So we have our core. Steal this line. We'll throw parent in here. How do we set parent? We're going to do it in pretty much the same places we're doing things now, but we need to be a little careful. How do we know that we have a parent variable that we can set? Go ahead.
Could you set parent equal to pivot right before pivot?
Yep. So don't change pivot until we first preserve parent. Make sense? So, well, don't change pivot until we first preserved pivot in parent. So go into our binary tree. We'll say BSTCore dot parent is equal to BSTCore dot pivot. Now we might have just set it equal to null first couple times through or something, but that's not going to hurt anybody. Okay, but before we change pivot to be the next guy down, we're going to remember the parent. Make sense? All right. What about grandparent? Same thing? Same thing, but relative to parent? All right. So now we're keeping track of all of those things. All right. So now, if we have determined that we're out of balance, which we've done at this point, right? That's back here in BST, right? I think it's in BST. Is out of balance, returns the root guys out of balance, and then how are we out of balance? So this is the string out of balance secondarily, blah, blah, blah. So this ultimately spits out how we're out of balance. We need to go ahead and, for right now, let's just call rebalance, but we'll assume it's left for testing purposes right now. So we're going to do public void rebalance. All right, now, for right now, we're going to assume we're only calling rebalance in the event that we're out of balance, and we're assuming we are out of balance left, left. That's how we've currently staged our tree. Okay, so how do we rebalance? Well, this goes back to our algorithm now. We've identified all of this crap. All right, we're keeping track of all this stuff. We also need to store our top level binary search tree. Let's go ahead and do that before we forget. So here's our core. So static BST, the tree, we'll start that guy off at null. And then inside of BST, after this guy is born, we'll go ahead and say BSTCore dot the tree is equal to this. So we'll preserve him. Okay. So we stored the tree. We got the culprit, the pivot, the parent, and the grandparent. We have all the pieces that we need for rebalancing now. So now we need to actually rebalance. What does rebalance require? Okay, well, we've identified the pivot. We have to ask the question, if we have a grandparent, okay, so if grandparent is equal to, well, it's not equal to null, then we're going to set grandparent's left child to pivot. So let's go back here to rebalance. If BSTCore.grandparent is not equal to null, if we actually have a grandparent, if we're able to go that far down, then we're going to say BSTCore.grandparent we don't have a way of setting a left child, so we need to go ahead and give ourselves setters for our tree here. So I'm just going to right click, generate setter for left tree and right tree. So now we have those guys. So dot set left tree for our grandparent equal to what? BSTCore dot pivot. So let's write this in. If we have grandparent set his left tree to pivot, and we'll keep going down that road for a second. If we do not have grandparent, we'll fill that out in a moment. So if we have a grandparent, we'll set the left tree to pivot. So that makes this guy, he's kind of hanging out in limbo for a second. And we've effectively moved that guy there. And then we're going to add parent to our pivot. All right. Now, do we know for sure that pivot does not have a right child? Pivot could have a right child. So we need to actually, we're not going to set pivot's right child to parent. We need to add parent to pivot, which means we need to teach our trees how to add a binary tree. Right now they know how to add char payloads. We need to be able to add a binary tree, which is pretty much going to be the same logic, but we're going to have to unwrap our payload here. So let's just minimize this. Set left, set right. There's their depth. All right, so here's our add. So we're going to have another version of add. Public void add binary tree. Okay, now we know we're only adding trees in the event that we're moving stuff around. So we don't need to keep track of all this grandparent and parent and pivot stuff in here. We're in the process of rebalancing. We know those guys will get reset the next time we decide to destroy our tree's balance. Okay, so when we're adding a binary tree, what are we going to do? We're going to ask all these same questions. So let's just steal most of this and we'll update it. Okay, so if tree.getPayload, actually we just say tree.payload, that'll work because we're inside the binary tree class. So even though this is a private member, we have access to it. So we're going to say tree dot. Get rid of this culprit code here. We would never build a new binary tree. Instead, we would just set it to tree. If it should go to the left, we'll just go ahead and set our huge tree we might be hanging on to here to the left. Else, we're going to add tree, which we'll call this version of add. Okay, so we have two add functions that have the exact same name but a different parameter type. What's that called? What's the object-oriented term when we have more than one method with the same name but a different number and or type of parameters? Polymorphism. So here's an example of polymorphism. We have two different add functions, one that takes a char, one that takes a binary tree. So when we call add here and we happen to pass in a binary tree, Java is going to know that I mean this version of it. All right, else if right tree, we'll set the right tree to tree. We're not going to keep track of culprit in here. Otherwise, we'll add the tree. All right, so we just added an ability to our binary trees that allow us to add trees to that guy. All right, so over here we say if we have a grandparent set as left tree to pivot, then we're going to add parent to pivot. All right. So we're back to our rebalance. So we're going to say BSTCore dot pivot dot add BSTCore dot parent. We'll add parent to pivot. All right. So add parent to pivot. So what that just did is in our little example here, that dropped parent right there. We'll just say that's good enough. All right. And then we're done. That's for our left. So parent still has an arrow that points up to this guy. Even though we've unlocked him from that, parent still. So now we have created a kind of an infinite loop inside of our tree, right? So when we set the left tree to pivot, we also want to go ahead and set parents left tree to null. Undo his left tree. All right, so that disconnected that. Then we'll add to our core, then we'll add our parent to our pivot rather. Okay, so grandparent existed. We made grandparent point to pivot. We made parent no longer point to pivot, so this guy's kind of free and clear. He might have stuff hanging off the bottom of him, but we're free and clear. Then we'll go ahead and drop this tree back onto pivot and let it plinko down. We happen to know in this case it'll bear right, at least initially, right? And that's our rebalanced tree. That's if we had a grandparent. If we didn't have a grandparent, so let's shift everything up one. So let's, oh, same problem. So we're going to go ahead and we're going to set grandparent here. We're going to set parent here. We'll set pivot here. We'll set culprit here. Get rid of those. Get rid of those. All right, so now we have a tree that looks like this. If we don't have a grandparent, what do we need to do? Because right now there's actually two things pointing at parent. One is parent, and the other one just happens to be BST's root. Just happens to be that guy. Make sense? All right. So if we don't have a grandparent, that means that we know that pivot should be the new root of our tree. All right. Pivot is new root. So what do? We set, well, actually we can do it up here in the top line. Set BST's root to pivot. Set parent's left tree to null. Add parent to pivot. So the other things are the same, but we do change what we do to pivot. Go back in here. This is what we do to pivot in the event that we don't have, or that we have a grandparent. These two guys remain the same. Else BSTCore dot the tree dot root. Do we make that public? Oh, we are in there. Okay. Dot root is equal to BSTCore dot pivot. So that'll update our root to point to pivot. Then we'll disconnect our left tree, and then we'll go ahead and add our parent. Okay, so let's test this. We know this guy is currently out of balance. Let's see, these were just our print lines. We can get rid of those. So we'll build our tree. After each time, we'll ask the question, are we out of balance? This should be true. we're checking around the A. We'll update that, but the answer is yes around the A. So what will we do? We're going to say tree dot rebalance, and then we'll ask, are we still out of balance? So we should get true left left, and then we should get false, and then nothing, because we're rebalancing in the middle. So, oh, and it was just left over from the left-left thing before. So, true, we're out of balance, left-left. We rebalanced, and now it's false. We're no longer out of balance. And this was just left over. All right. So that's for left-left, and let's go ahead and just test it for our other one. So this would be GFA, would be our GFA, still on A, so this should be out of balance left left, and then not out of balance. So same result, but our root node should have changed in this case. So true left left, false. Oh, interesting. Why didn't the second one, why did it still print out of balance left left? Because we got a false from it, so it gave us the right answer for whether we were out of balance. Oh, it's just because we're at it was at the root node. All right, so we passed in A. It's not less than, well, it is less than or equal to it, so we went to the left. No, we didn't even try it because we didn't print out anything. Are we out of balance? How are we out of balance? Rebalance. Are we out of balance? How are we out of balance? So it worked the first time. We pass it back in with the A. Okay, so then we assume it's left. Let me run this again. I don't see how that's even possible for it to not print it out the second time. Yes, we're out of balance, left, left. And then no, we're not out of balance. Oh, yeah, so out of balance here, so that's that call. And then how are we out of balance passing in an A? Oh, it crashed. So it must be crashing because this dot root we passed it A. I actually think it's working, but I just want to see why it's, when we reset root, I don't think we're crashing here. Let's just print out root there, so we should get an actual value, not a null. Yeah, so we get an actual value. So our root is set correctly. So it has to be that we're going back in here. So what we'll, and it's because we've moved the A higher up in the tree, so determining how we're out of balance is not really an issue. So now we'll say just this, if tree dot is out of balance, we'll print out that. Then we'll rebalance our tree, and then we'll print out how we're out of balance. We should be a false here. We know we're going to be a false here. So now it shouldn't crash anymore because we're not going down a path after we rebalanced. All right, so questions about what we did here? So what I'm going to do is I'm going to push this code up. So go ahead and pull this code down, add the right case to this code using the way that we solved this problem here with our 4 singletons. Make sense? Shouldn't be overly difficult. Should be very, very, very similar to the left. But add the right case and make sure you call the correct thing inside of rebalance here. Right now we're assuming left out of balance. You're going to have to add, are we left or are we right? And we already have a function that determines how we're out of balance. So you don't even have to just call the function and interpret the result. Make sense? All right. So I will see everybody on Thursday.